In the last class we talked about the tension force due to a string. A string is inextensible. That means the length of the string is fixed. If you try to stretch this string offers some resistance in the opposite direction which prevents the string from getting stretched. So this resistance is what is called the tension force due to a string. Now if you have a string which is stretchable, just a rubber band, right, it is stretchable. So this is the natural length of the string, but it can be increased if you apply force, right. Now once it is a stretchable string, so that is no more treated as a string in physics, right. It is more like a spring, right, except that it cannot be compressed, but it follows the rule of a spring. See here, this is the natural length. Now it can be increased. Even this stretchable string offers some resistance, but this resistance is not as strong as that of the string, right. See here, initially it is easier to stretch, right, easier. I am applying the same amount of force, but as the length increases, it gets harder and harder to stretch this further, right. So that means it is a variable force. Unlike the force due to a string, this is the variable force. Suppose it is an unstretchable string, right. So like this, okay, inextensible. So string. Now if you apply a force, the tension force due to the string is also of the same magnitude as the applied force, right. So that is fixed. For a particular force, the tension force is fixed. If you increase the force, the tension force will also increase. But for a constant force, the tension force is a constant. But if it is a stretchable string or a spring, okay, the spring force is not a constant force. Even if you apply a constant force, right, constant force, as the length increases, the force will also increase. The force depends on the length, alright. So it is a variable force. So that is one difference between spring force and the tension force, right. So take this example. See, this is a massive spring, right. Our Chintu is trying to compress the spring, right. So now initially the natural length of the spring is L. Now it is reduced to L minus X. So X is the compression, right. Yes. Now this spring will always try to regain its shape. That means it will always try to get back to its original length. So it is compressed now. So the spring will apply a force in the opposite direction, right? In the opposite direction. So in the direction of its natural length. So the force applied by the spring on that person is in this direction. On the other hand, if you elongate the string, right? Spring, right? If you elongate the spring, so that means the length has increased. Now again it will try to get back to the original length. That means the force applied by the spring is in the opposite direction, right, in the direction of its natural length. So whether it is compressed or elongated, so the spring will apply a force of equal magnitude only in both the cases. If the compression or elongation is X, it will have a force of equal magnitude but in opposite direction, right. Yes. Now we will write few points about this spring force, okay. Yes. So let us write few points. See, first of all, this spring force is proportional to the compression or elongation, right. So that is the first point. See, this is about the spring force. So the force due to this spring, so that is proportional to this X. X is the compression or elongation. See, sometimes it is written as delta X because that is a change in the length of the spring. Sometimes written as delta X, but let us use this X only. X is the compression, not the total length of the spring. That is L, constant. But this is only the compression or the elongation of the spring. Alright, yes. So this rule is called by the name Hooke's law. Okay, so Hooke's law is what? The force due to the spring is proportional to the compression or elongation, right? Yes. Now, the Hooke's law doesn't work always, right? It fails in some cases. But about those cases we are going to discuss later, right? In a different chapter. But here, in this chapter, Hooke's law always works for a spring, right? So force is directly proportional to the compression or elongation, right? Yes. Now, so that is the first point. So once the force is proportional to X, then the force can be written as some K multiplied by X, right? Some proportionality constant, right? So it is proportional. So F can be written as K times X. Okay. Yes. What is this K, right? So this K is called by the name, okay, we can call it spring constant, right? Spring constant. The spring constant K, right, can be written as force divided by X, right, from the same formula. So F divided by X, right? Yes. So what is the unit of this K, right? We know that, right, force divided by length. So that is Newton. This is meter, right? Newton per meter. So that is the unit of Newton per meter. So that is the unit of this K. So this K Alright, that is called the spring constant for that particular spring. So that depends on the material geometry of the spring, right? So that is fixed for the particular spring. So that is the spring constant. So our required force is proportional to this x. That proportionality constant is k, which is called the spring constant. Okay, sometimes it is written as minus kx, right? Here we are writing only the magnitude, right? Not the direction. Direction is already known. In the first case, the direction is in this direction, positive direction, because it is compressed. So the spring will apply force in this direction. So that is positive. Now in the next case, so the force due to the spring is in this direction, right? So when x is negative, the force will be positive. When x is positive, like in the second case, then the force is in the opposite direction, negative. So that means this can be written as minus kx also, right? So, but we are not writing that, we are only writing the magnitude, but the direction can be decided, right, depending upon the situation, right? So direction can be understood, but this is only the magnitude. Is that okay? Yes. So F equal to kx. Yes. Alright. Now just one more point we will write about the spring force, or about this spring constant. For a particular spring, right, for a particular spring, this spring constant is inversely proportional to the length of the spring, right? The longer the spring is, less is the value of the spring constant for that particular spring, right? So we can write it as, or we can write it as KL. So KL equal to constant, okay? KL is a constant for that particular spring, right? So if you reduce the length of the spring, right, then the value of k will increase, right? It is inversely proportional for the same spring only, not different spring. If you cut the spring into two equal halves, so the k value will double, right? So it will become twice. So KL is a constant value. See, these are the only points that you have to know about spring force, nothing else, right? We're just going to use this formula, right? The force equal to k times x, maybe this result, right? Let us use these basic results, right? So only these points to do some questions, okay? See, just for illustrative purpose, we have used a massive spring, but all the springs in this chapter are massless springs, right? You can safely ignore the mass of the spring. So the springs that we are going to consider in this chapter are very small and massless, okay? Here, a spring of spring constant k and length L is cut into two parts in the ratio m:n. We have to find the spring constant of each of these parts, right? We know that for a particular spring, the spring constant multiplied by the length of the spring is a constant value, right? So k multiplied by L is constant. So KL is constant for a particular spring, right? Yes. Now we have to find the lengths of these two parts of the spring, right? So what is the length? The total length is L, that is divided into two parts in the ratio m:n. So what is the length of each part? See, length of these two parts. So the total length is L, that is divided in the ratio m:n. So that means each part has length. See, first one, so m divided by m plus n multiplied by the total length L, right? So that is the first part, right? Similarly, the next one, so that is n divided by m plus n multiplied by L, right? That is how we split this in the given ratio, right? m:n, right? Yes. If you can't write this directly, so we can do this. So the ratio is m:n. So that means each part can be taken as, the first part can be taken as mx. The second part is some n, okay, x. Because the ratio is m:n. So that means first part is m multiplied by something. Second part is n multiplied by something. But this is the total length. So that total length is L. So that gives you the value of x. So x equals L divided by m plus n. So that is the value of x. So that you can substitute back here. So what is the first part? So our mx equals, so m divided by m plus n multiplied by L. So that is the first part. Similarly, the second part is nx. So n multiplied by, so L by m plus n. So that's what we have written here directly. So we have got the lengths of each part. That means we can use this relation. What is that? KL is constant for the whole spring and the first part of the spring, the next part of the spring, right? So we equate them, so we get the answer, right? Yes, KL equals, so this is for the total spring. So that equals for the first part of the spring. So that is K1, right? Let us take the spring constant to be K1 multiplied by the length of that part. So that is ml divided by m plus n. That equals the second part now, right? So that has spring constant, say K2, and this length, so nl divided by m plus n. Alright, so that's all. That will give you the value of K1, right? Equating these two, we get the value of K1. So K1 equals, alright, so multiplied by L gets cancelled. So this is K multiplied by M plus N divided by M. So that's all. This is the value of K1. Similarly, so you can find K2 equating these two expressions, right? Yes. Now, so this K2 equals, so K multiplied by M plus N divided by, right, divided by N. So that's all. So these are the spring constants of these two parts, right? As a particular case, if this spring is cut into two parts in equal ratio, right? So 1:1, right? Which means equal parts, right? Now what will happen? So M is Tn, so that is 1:1. So that means K multiplied by 2. That's all, right? So 2K, which means if you cut a spring into two parts, equal parts, then the spring constant is double, right? It becomes twice the value, right? So initially the spring constant is K, right? Now it is cut into two parts, equal parts, then the spring constant becomes 2K, right? 2K and 2K. Do you understand? That is a particular case. Generally, when the ratio is M is Tn, so these are the spring constants of these two parts. Okay? Yes. This time two springs with different spring constants K1 and K2 are joined, right, end to end. Now we have to find the combined spring constant, right? Now here this is called a series combination of two springs, right? Two springs are joined end to end, right? So that means we have to find the combined spring constant of these two springs. Okay, yes. Now what do we do? So first L1 and L2 are the lengths of these two springs, right? Now when they are joined together, so that means the length will become L1 plus L2. That is the total length of the spring now. Okay. So initially K1 and K2 are the spring constants. Now when you apply a force F, right, in this direction, now each of these springs will expand, right, which means it will get elongated, so by length X and Y. Okay, X is the elongation of the first spring and similarly Y is the elongation of the second spring. Now the combined spring will also get elongated, so that length is taken as Z. That means Z equals X plus Y, right? Because so X plus Y is the total elongation, so that is same as Z. So that means, so we have this relation Z equal to X plus Y. Okay, yes. Now but we know that the spring force, right, the spring force F equals K multiplied by X, right, the spring constant multiplied by the elongation, right? So this relation we know, right? So that F, the spring force, is same as the force, external force, right? Because the force is applied in this direction, the spring force will work in the opposite direction. They have the equal magnitude, right? So F equal to Kx. So that means what is the value of X here? So X equal to F divided by K. So the elongation is the force divided by the spring constant. Okay, yes. Now in the first case Z, the second case Z is the elongation. So that means what is the value of this? So that equals force divided by the spring constant, right? So force is F divided by the spring constant is K. Okay, yes. Now X, similarly first spring, for the first spring same formula works, right? Force divided by spring constant, but the force is same F only, divided by the spring constant is K1 plus similarly Y. So that as force divided by the spring constant, that is K2, right? This is the relation. So 1 divided by K equals, right, yeah, so 1 divided by K equals 1 by K1 plus 1 by K2. Okay, so that's also, that is the relation, right? So the effective spring constant, so that is K, can be found, right? So you can multiply, so K1 K2, K1 plus K2. Okay, so K can be written as, so this is K1 K2 divided by K1 plus K2. So that's all. So this is the effective spring constant of the combined springs, right? Yes, K equals K1 K2 divided by K1 plus K2. Is that okay? Yes. Now we can generalize this, right? Instead of two springs, if you join several springs, right? So n springs, okay, but in series, right? They are connected in series like this. Then, so generally, so this formula can be used. So generally, the effective spring constants 1 by K. So this formula can be generalized. So 1 by K equals the spring constant of the first spring. Similarly, for the second spring, 1 by K2, etc. 1 by Kn. Okay, so this formula can be used for series combination of two springs. So this can be remembered as a formula. Okay, so remember this, many springs are joined in series like this. okay, in series like this, then the effective spring constant is simply this, right? This formula, the reciprocal of that equals the sum of reciprocals of all the spring constant. Okay, so this is the general case, but for this particular case where two springs are joined, so the answer is this one, K1 K2 divided by K1 plus K2. Okay. Here we have two springs connected in parallel. This is a parallel combination of two springs, unlike the last question where the springs are connected end to end. So that means series combination. Here the springs are connected in parallel, right? This is a parallel combination of two springs. We have to find the effective spring constant, right? Same thing, you have to apply a force in this direction. So the spring force will be in the opposite direction, but the spring force here is due to these two springs. See, these two springs are connected in parallel. That means the elongation of the first spring is same as the elongation of the second spring, right? So same extension. That means x units here also. So the force, external force in this direction equals, right, in magnitude, right, the force exerted by these two springs, right? Yes, that means the force in this direction, that is F, that equals the force due to these two springs, that is in the opposite direction but the same magnitude. So what is the force due to the first spring? So that is, say, K1x, right? X is the elongation and K1 is the spring constant, plus the force due to the other spring, right? So that is K2, same x, right? The elongation is same because they are connected in parallel, so they'll extend, right? They'll elongate by the same length, right? Yes, that's it. Now, so we have to find force F. Now the next case, the effective spring constant. Suppose these two springs are combined, we consider them as one string. So the elongation here is same x, right? X is the same elongation, right? So here also, in that case, what is the force? So that time the force equals K. K is the effective spring constant multiplied by the elongation. So also in the next case, the same F equals K multiplied by the elongation. So K multiplied by x. So K is the effective spring constant. So these two can be equated. So this implies, so we can equate that. So Kx equals K1x plus K2x. So this is very simple. So K equals K1 plus K2. So we simply have to add these spring constants, right? So that will give you the total spring constant in the parallel combination. Okay, or we can we can generalize this. Generally, if many springs are connected in parallel like this, so the general spring constant, the total spring constant is the sum of all spring constant, right? K1, K2. So this should also be remembered, right, as a formula. So two springs are connected in parallel, or any number of springs are connected in parallel combination like this, then the effective spring constant is the sum of all spring constant, right? So in series combination, so we have that relation 1 by K equal to, so 1 by K1 plus etc. 1 by Kn, right? So this relation, so you have to remember, right? So spring combinations, right? Parallel combination and also the series combination, we have the effective spring constant having this formula. Okay, yes. Here a block is connected to three springs. This block is displaced by x units to the right or left. We have to find the acceleration of the block. Force equal to mass times acceleration. That will give you the required acceleration. But what is the force here? The force is due to all the three springs, right? So let us find the total force exerted by these three springs on the block, and then force equal to mass times acceleration will give you the required acceleration. But what is the force on the block due to the first spring? These three springs are connected in series or parallel. It looks like these two springs are connected in parallel and the third spring is connected to them in series. But actually all the three springs are connected in parallel only, because the block is in the middle, not at the end, right? So now we'll go back to the basics only, right? So this block is displaced by x units to the right, okay? Now the elongation of the first spring is x units, okay? That means what is the force? The spring constant multiplied by x. So that means the force here is due to the first spring, right? So we are going to use just this formula, force equal to mass times the acceleration. But force is due to the first spring, right? First spring is what? So K1, that is spring constant, multiplied by the elongation, that is x, plus now force due to the second spring. So that has the same elongation, right? Because same, they are connected in parallel, so same elongation, but K2 is the spring constant, so that means K2 multiplied by x. Okay, now force due to the third spring. Now the third spring is compressed by x units. Whether compressed or elongated, the spring force is constant, right? Same value, right? Because the elongation is x or compression is x, the spring force is k multiplied by x. But the direction is opposite. See, what is the direction of the force due to the third spring? See, the spring is compressed by x units in this direction. That means it will try to get back to the natural length. So that means the force due to the third spring is in this direction, negative x direction. What about the force due to the other two springs? So these are elongated in this direction. That means the spring force is in the opposite direction, the negative x direction, which means all the three springs exert force on the block in the same direction, this direction only. So that means the force due to the third spring also in the same direction. So that means plus only. So plus k3 multiplied by x, right? Yes, same x in all the three, right? And also direction is also same, only the spring constants are different. That's all. This is the total force exerted by these three springs on the block. So that must be equal to mass times the acceleration. Okay, yes, that's it. That will give you our required acceleration. So acceleration equals, so k1 plus k2 plus k3 multiplied by x divided by m. So that's all. So this is the acceleration of the block. Okay, but see this formula, force is what? A multiplied by m, that equals kx. So the k, effective k is k1 plus k2 plus k3. That means it is like these three springs are connected in parallel like this, right? They are connected in parallel. It will have the same effect. Okay, though it looks like series combination, but so because the block is in the middle, so these three springs are connected in parallel, then they'll have the same effect, right? K1 plus K2 plus K3, that is the formula for the parallel combination, right? So that's all. So this is the acceleration of the given block, right? So K1 plus K2 plus K3 x divided by m. Okay. Here a spring is connected to a pulley and a block is attached to a string, and some setup is given. We have to find the extension in the string in the equilibrium position, right? Yes, now what are the forces acting on the block, right? Let us find one by one. Okay, block. So the forces acting on the block are the gravitational force in the vertically downward direction, right? Gravitational force mg in the downward direction minus the tension force due to the string. So that must be equal to 0, right? Total force is 0 because the block is in equilibrium, right? So that is done first for the block. Okay, now for the pulley. What are the forces acting on the pulley? See, tension force, these two sides of the string, T plus T, 2T is the total force acting on the pulley in the downward direction. So 2T is the total force in the downward direction, and also in the upward direction we have the force due to the spring, right? So suppose the extension is x and k is given, right? So k multiplied by x is the total force due to the spring in the upward direction, right? That means minus kx. So this is the total force. So that must be equal to 0 because again it is in equilibrium, or the mass of the pulley is anyway 0. So 2t minus kx is 0. Now that's all. Substitute t here, you will get the required answer. That's it. So this gives you the value of x is what we need. So x equals 2t divided by k, but t is already known. T is mg. So 2 mg divided by k. So that's all. So that is the required extension, right? So the elongation of the spring given there. So that is the answer, 2 mg divided by k. Okay. Here we have two blocks, one moves in the horizontal direction and the other one moves in the vertically downward direction with the same acceleration. The acceleration of this block and that block are same, okay, but the directions are different, and these two are connected by two springs. But these two springs are connected in series, right? So though they are not along the same line, but these two are directly connected by a string, right? That means these two are connected in series. Now we can find the effective spring constant, right? So for series combination, so what is the series combination? These two springs are connected in series. So that means this is the formula, 1 by k equals 1 by k1 plus 1 by k2. So k1 here is say 500. So 1 by 500 plus 1 divided by 750. Alright, so simplify this, you get the value of the k, right? Which means if you combine these two springs and made it into one spring, so that will have spring constant, this value k. Alright, so what is this value? So this equals 1500 this is 3 plus 2 5, so that is 1 by k, so that gives you the value of k, so that equals, so 300, okay, 300 Newton per meter, so that is the value of k, right, the spring constant. Okay, now let us take one by one the 3 kilogram block. Okay, so 3 kg block. What are the forces acting on this block? What are the forces acting on this 3 kg block? So the gravitation force is acting in the vertically downward direction, so mg, so that means 3g, minus the force due to the spring in the vertically upward direction. See, we have combined these two springs and made it into one spring. Now the force is only due to that spring, right? So what is the force? K multiplied by x. If this is confusing, you take it this way. Okay, now we made the vertical portion of the string into horizontal like this. That means the gravitational force is acting in this direction, right? Positive x direction. So gravitational force in this direction, 3g, minus we have the spring force. So what is spring force? K multiplied by x. So k is already known, so that is 300, right? That is the combined the spring constant of these two springs, right? So that means 300 multiplied by x. So x is the elongation, so 300 multiplied by, this is the total force on the 3 kg block, so that equals mass times the acceleration, so 3 multiplied by the acceleration. Similarly, for the 5 kg block, for the 5 kg block, what are the forces? That is already moving in the horizontal direction only, so the only force here is due to the spring force, right? Yes. Now what is the total force? So that is same thing, right? 300 multiplied by x, so that is the total force. Okay, so that equals mass times the acceleration, so mass is 5 multiplied by same acceleration, that's what is given in the question, right? The acceleration of both the blocks are same, 5 multiplied by a. So if you solve this, so we get the value of the acceleration, right? So this implies our required acceleration equals, okay, so you can simply add these two, right? 3g, this gets cancelled for 8a, so a equals, yeah, 3g divided by 8. Okay, that's all. So that is the acceleration of both the blocks. Okay, done, acceleration. Now we have to find the elongation of that vertical spring, right? That means the spring constant 750, so that the elongation we have to find. Okay, now for that 3 kg block we have to do it separately. Now let us take the first case only. The first case, before we combine these two springs, see what is that case, right? So what are the forces acting on the 3 kg block? So this time the 3 kg block, again the forces acting on the 3 kg block, when we consider, right, we consider these two springs to be separate. Okay, now what are the forces acting on the block? So 3g in the downward direction, 3g, minus spring force. So what is the spring force here? So 750, k is 750, so 750 multiplied by the elongation, right? So not the same elongation, because that is a separate spring now, so that is, say, some x1, you can take x1, alright, kx, right, 750 x1, so that equals, so mass times the acceleration, so mass is again 3 kg multiplied by the acceleration, so that we found here, right? So a, okay, so 3 times the acceleration, so that is 3g divided by 8. Now we can find the value of this x1, right? So simplify this, this is 3g minus, this is 9g by 8, so that means 24 minus 9, so 15g by 8. So 15g divided by 8, so that equals 750 x1, so that will give you the value of x1, right? So that is, you can take the approximate value of g to be 10, right? So 150, 750, so that means 5 times, so 5x1 equal to 1 by 8, so that means x1 equals, yeah, so 1 divided by, so 40, so 1 by 40, okay, meter. So that's all. So that is the required, the value of x1, right? That is the elongation of the spring. So we can convert that into centimeter, right? So that is, so we can multiply this by 100, right? Right, centimeter, converting it. So 100 divided by 40, right? So 10 by 4 are 2.5 centimeter. Okay, so that's all. So that is the elongation of the spring, right? That vertical spring having spring constant 750, that has spring constant, that means the elongation, so that is 2.5 centimeter, so that is the answer. Here the mass of the object as read by the spring balance is 6 kg. So 6 kg is the mass of the object, but the spring balance does not read the mass of the object directly, it will only read the the elongation, right? So using the elongation, it will calculate the mass of the object, right? See, it is like this. See, the object is in equilibrium. So that means, so the total force, right? So mg minus the spring balance, spring force. So that is kx. So that must be equal to 0, right? So that means, so if you want to find the mass of the object, okay, so kx divided by g. Okay, so that is the reading. The spring balance reading is simply this one. So it will only read x, right? That is the elongation. Multiply that by k, divide by g, you will get the mass of the object, right? Yes, that's it. So in the first case, the mass of the object is 6 kilogram. Okay, what about the second case? See, it looks as if there is a mass of 6 kg that side and there is a mass of 6 kg this side. So the total mass is 12 kg, right? Right? No, it is not like that. See, the elongation of the spring balance in the second case, what is that? What is the total force acting on the 6 kg block? See, in the 6 kg block, any one 6 kg block, you take 6 kg block, what is the total force acting on the block? So that is, so mg in the downward direction, so mg, so 6g, minus the force due to the spring, so that is kx, right? So same kx only, so k multiplied by x. So that is the total force, so that equals 0. So that means, what is the value of kx? So that equals 6g. So kx is 6g. So that means, what is the reading as per our formula? So the reading is, reading will give you the mass of the object. So what is the reading? So that is kx divided by g. So kx divided by g. So that means 6g divided by g. So we are getting the same answer, 6 kilogram only. In the second case also, the answer is 6 kilogram, not 12 kilograms, because you know, see, the other mass, right? So one block has mass 6 kilogram. The other end is attached to another mass, right? Same 6 kilogram mass. So this is only a support, right? If this mass was not there, so there will be no tension in the spring balance, right? So that will fall off, right? So this is only a support, right? So that means it is only 6 kilogram, that is the reading of the spring balance, right? Okay, same 6 kilogram, so both in the first case and also in the second case, right? So that is the answer. Here we have two spring balances, we have to find their readings. So like we did in the last question, what is the reading of the spring balance? We just need the elongation, right? So kx divided by g will give you the reading of the spring balance, right? See, the mass is directly attached to the spring balance, so kx divided by g is the mass of the object, but that's not the case here, right? It is not directly attached to the spring balance. Now let us find the elongation in both these springs, so that will give you the reading, right? Yes. Now let us consider these blocks one by one. So this 8 kg block, what are the forces acting on this block? So gravitational force in the downward direction, and it is attached to a string, right? So tension due to the string, so 8 kg block. So the gravitational force, right, 8g in the downward direction minus the tension in the upward direction, so tension in the string, so that equals mass times the acceleration, 8 times the acceleration. Okay, so that is for the 8 kg block. Okay, done. Now 2 kg block. So for the 2 kg block, again it will move in the upward direction, right, with the same acceleration as that of the 8 kg block, right? So but in the opposite direction. So tension in the upward direction, so T minus gravitational force is 2g, that equals the mass times the acceleration, so 2 multiplied by the acceleration is same a. Okay, this will move up, so that will move down, right? So with the same acceleration. Okay, done. So this will give you our required tension and acceleration. I think we need the tension, right? So let us find the tension. So we can substitute the acceleration here to find the tension. This gives you what can be done. So multiply this by 4 and then subtract. Okay, multiply this by 4 and then subtract. What will you get? So that will be, so that will become 0, right? Multiply this by 4. So 8g, this is multiplied by 4 and subtract. So that is 16g. So minus t minus 4t. So minus 5t. Okay, so this becomes 0. So equals 0. So the tension here is 16g divided by 5. Okay, so tension in the string. Okay, now we have to find the tension in the spring balance. Okay, that means kx we have to find, right? Let us find kx. Now for the pulley, so let's consider that pulley. For that pulley, what are the forces acting on the pulley? tension, right? The two parts of the string. So tension in the downward direction. T plus T. 2T is the total tension acting on the pulley in the downward direction, right? 2T. Minus the force due to that spring, right? Force due to the spring in the upward direction. What is the force due to the spring? So that is, okay, so that has spring constant, say K2, right? That is the second spring constant is K2 and the extension is X2, so K2 X2. So that is the force due to that spring, K2 X2. Okay, this is the total force, so that must be equal to 0 because pulley is at rest, it is massless, so 2T minus K2 X2, so that equals 0. Okay, now so we can find what is the formula for the reading, that is Kx divided by G. So that means the reading equals, so here for this spring, so the reading is K2 X2 divided by G. Okay, K2 X2 here, Kx, so K2 X2 here. So but K2 X2 is 2T, so 2T divided by G. But what is the value of 2T? We have already found T, right? What is T? 16G divided by 5. So 2T is 32G by 5. 32G divided by 5 again divided by G, so that will give you the value. So G gets cancelled, 32 divided by 5, so that is 6.4 kilogram. So that's all. So that is the reading, right? That is the mass as read by the spring balance, right? The second spring balance. Okay, similarly we have to find the reading of that spring balance also, right? So for that, so the other pulley, okay, so what are the forces acting on the other pulley? So that pulley, what are the forces? There is a force due to the spring, right? So below that, right? That is in the downward direction. So that is K2 X2. K2 X2 in the downward direction. So K2 X2. That equals the force in the upward direction. What is the force in the upward direction? There are two tensions, right? Tension this side and tension that side. But these two tensions are same. But the tension on this side of the string, so that is due to that spring, right? So what is the extension? So that is say X1. So K1 X1. So that is the tension here. So K1 X1. K1 X1 is the tension on this part of the string, right? Because that is attached to a spring, so the spring has force, so K1 X1, right? So that means the other side also we have the same force, right? Because it should balance, otherwise this pulley will rotate. So these two balance. So that means, see this force on this part of the string attached to the spring, so that has value K1 X1. So the other side also the same value, that means 2 times this one. So 2 K1 X1. Okay, right? So these two balance each other. Now you see, now what is the reading? Kx divided by G, same formula, but here K1 X1 divided by G. So our reading here is K1 X1 divided by G. Okay, K1 X1 divided by G. But what is K1 X1? K2 X2 divided by 2G. Okay, K2 X2 divided by 2G. But K2 X2 divided by G is already found. Okay, so that is 6.4 kilogram. We can directly substitute. K2 X2 divided by G is 6.4. So if we directly substitute that value, so divide by 2, so 3.2 kilogram. So that's all. So that is the reading in the spring balance in the top, right? So these two are the readings. So one spring balance shows this result, right? 6.4 kilogram. The other one has result 3.2 kilogram, right? So that is the answer. Here a block attached to a spring is moved in the horizontal direction by a distance of d units. Now we have to find the time taken for the block to get back to its original position. That means the time taken for the spring to get back to its normal state, right? So the normal length. Okay, so let us find it. See, this is a very simple question if you know simple harmonic motion, right? So it is something related to the time period of the simple harmonic motion, but we are not going to use any concept of simple harmonic motion. We will simply use our idea of spring force, right? So obviously this method is a little complicated, but for now we only know spring force, nothing else. So let us use only that to get the answer. Okay, yes. Now what is the force? Now the total distance is d. Now let us take some intermediate position. Suppose the elongation is x is a variable, so elongation is x. So that means what is the force acting on this block? So that is kx, but in the opposite direction. Take this direction to be positive. That means the force is acting in the opposite direction, negative direction. Minus kx is the spring force on the block. Okay, so that means, so we have the formula for the force. So that is So force equals minus kx. Okay, so that is the force. Now from that we can find the acceleration. So what is the acceleration? So the acceleration equals force divided by mass. Okay, force by mass is the acceleration. From acceleration we are going to find the velocity of the object by integration, right? So what is acceleration? dv divided by dt. That is the rate of change of velocity, which is the acceleration, right? dv by dt is the acceleration. Okay, so that equal, but to get the value of v, obviously we have to do the integration. Okay, but there are three variables. You see, v is a variable, t is a variable, x is also a variable. So we reduce it into 2, then only we can do the integration of both the sides. So what do you do? dv by dt can be written as dv by dx, okay, multiplied by dx by dt. dx by dt. Okay, that is a chain rule of differentiation, right? dv by dx, dx by dt, that is same as dv by dt, or if you cancel this, then also we'll get dv by dt. So that equals minus kx divided by m. Now bring one variable to one side, like what is dx by dt? So that is the rate of change of the displacement, so that is the velocity. So dx by dt is v, so that is v dv. So this is v, so v dv equals, the other side we have minus kx by m, so this dx. Now we can do the integration, right? So let us do the integration. So initially the speed is 0, right? The velocity is 0 initially at the extreme point, right? 0, and at some point in between the velocity is say v. Okay, similarly initially the distance is d. Okay, x is d, right? That is the right extreme point, right? So d, and then at some point in between, so we have distance x. Okay, so now let us find, so this we can integrate, right? So this is v square by 2, v square by 2, so that equals, let's do the integration of this. This is x square by 2, right? K by m, x square by 2, so 2m, and x square you substitute the upper and lower limit, so it is x square minus d square, but there is a minus, so we can write d square minus x square. Okay, just integration and substitution of the limits. Okay, now this is v square. Now we have to find v, so let us find v. So v equals square root of that. So what is the square root? 2 gets cancelled. What is the square root of that? Square root of k by m, again square root of d square minus x square. But there is one thing we have to see. When you take the square root, it may be either plus or minus, right? Plus minus. Okay, but we should take here minus. Why minus? Because see, the velocity is in the opposite direction. This whole value is positive, right? This value. So we have to put a negative sign because the object is moving in the opposite direction, right? Negative direction. So velocity will be negative, right? So negative. Generally you have plus minus when you take the square root, but here we are taking only negative because we know the sign of v. So this is v. But what is v actually? V is the rate of change of displacement, that is dx divided by dt. So dx by dt is this value. Okay, yes. So dx by dt. See, if you don't put a negative sign here, so when you write dx by dt, so that is minus v. So there also we can adjust it in any case. So dx by dt is negative. Okay, so that is minus root k by m root d square minus x square. Okay, so that is dx by dt. We have to again do the integration to get the value of x. Okay, so let's do the integration. Dx divided by, so this function, right? So dx divided by, so this one, so root d square minus x square. So that equals, so here minus root k by m, so dt. Okay, yes. Now again do the integration, right? So this time, so we know the right end point, x value. So x value initially is d, right? So d. And then now we have x value 0. Okay, at the midpoint, right? The natural length of the spring, so the value of x is 0. Okay, so there also time taken we have to find. So initially the time is 0, now the time is t. Okay, so that should simplify, but you need to know some integration. So if you remember the formula, so 1 divided by root d square minus x square, so that has integration, so sine inverse of x divided by d. So that is the integration of this function. So now we have to substitute the limits. So d2 0, that equals, so here we can directly write minus root k by m, so that is t. That's all. So that's it. So this you can substitute here directly. Substitute 0 here, sine inverse of 0, that is 0. And d if you substitute, so sine inverse of 1. So sine inverse of 1 is pi by 2, right? So that means this is minus pi by 2. So that equals minus root k by m t. From this we can find the value of t, right? So find the value of t, that is pi by 2 square root of m by k. So that's all. So this is the required value of t, right? The time taken by this block to reach its initial position, right? So that's it. So that is the answer. See, this is directly related to the time period of the simple harmonic motion, right? But we're not using any idea of simple harmonic motion here. We use the simple idea of the force acting on the object. That's all. So that is the spring force. But that spring force happens to be a variable force. If this force or this acceleration is a constant value, then we could have used the basic equations of motion like s equal to ut plus half at square, right? But because this force is a variable force, right, the acceleration is variable, not constant, so we have to use the basic calculus, right, like the differentiation and integration, and finally we got the answer t. So that is pi by 2 root m by k. Okay. Here we have two blocks connected by a spring. A force F acts on that block in the horizontal direction. We have to find the maximum elongation of the spring, right? Yes. Now here these two blocks are free to move. The only force acting on this block is the force due to the spring. The forces acting on the other block are the force, applied force F, and the spring force in the opposite direction, right? Yes. Now we have to find the maximum elongation, right? Initially the spring is unstretched. Now it will have velocity 0, right? Initial velocity is 0. Now the force F starts acting on that block. Now we have to find the maximum extension, right? So when the maximum elongation happens, at that point of time, both the blocks move with the same velocity, right? Both will move with the same velocity, right? That is when the maximum extension happens, right? So if it is increased further, so the velocity will be different, right? So the maximum extension is when both the blocks move with the same velocity, right? So that is what we are going to use, right? Yes. Now what are the forces acting on these two blocks, right? Let us write all the forces. Now the block M, for the block M, so what are the forces acting on it? So that is only the spring force, right? Kx in this direction. Suppose at a particular instant of time, x is the elongation, right? X. So that means kx is the force. So kx is the only force. So that means kx must be equal to mass times the acceleration. So let us write it as am, right? The acceleration of that block. Okay. Now similarly the other block. So what are the forces acting on this block of mass capital M? So that is force in this direction, right? Force F minus the opposite direction. The spring force is acting in the opposite direction this time, right? On that block, right? In this direction. So minus kx. So that equals mass times the acceleration of that block. So that is m. Okay. Yes. This is the relation between the accelerations. Okay. Now let us find the accelerations of these two. See, when the maximum elongation happens, at that point of time the velocities are equal. That means the relative velocity is 0 at that point. Relative velocity, right? Which means the velocity of this minus velocity of that. So that is 0. So when you want to find relative velocity, so let us start with relative acceleration. Right? What is the relative acceleration? So relative acceleration. Yes, relative acceleration. That means you are observing this in the frame of reference of any one of these blocks, right? Yes, let us observe this from the frame of reference of that block of mass capital M, right? Yes, that means what is the relative acceleration? So this am is the actual acceleration of the block, right? This block. Now we want relative acceleration. That means minus the acceleration of the other block. So this is the acceleration. Alright, so this we can find. Okay, so that is taken as say some a only. So a is the relative acceleration. So that is the difference. So that is equal to, so we know that, right? So what is the value here? So am is found already. So this is kx divided by m minus, so similarly this one. So that is f minus kx divided by capital M. Okay, so that's it. Let's simplify this. So this is yeah, so what do you get? K m x. Similarly this is plus k small m x. So that if you simplify, so that is m plus m kx minus f multiplied by m. So minus m F divided by this m multiplied by m. So this is the acceleration. Okay, but what is acceleration? So that is the rate of, see, acceleration is a variable, not constant. If it is constant acceleration, as usual we can use the formula, right, the basic equations of motion, right, ut plus half at square something. But here acceleration is a variable value, right, x is variable, not constant. So that means you have to use calculus, right, you have to use differentiation, integration, right. Yes, acceleration. What is acceleration? The rate of change of the velocity, right. So dv by dt. Again, right, like we did already, there are three variables now. What are they? Velocity, time, and the distance, displacement x. So we want to get it in terms of two variables for integration. So what do you do? dv by dt can be written as dv by dx multiplied by dx by dt, right? Dx by dt is the rate of change of the displacement, right? That is v. Is that okay? So that's what we did already, right? Now v dv, so that can be integrated, so v dv. That equals, so that value, so this is m plus m kx, yeah, minus m f divided by m. Okay, so multiplied by dx. Okay, yes, so that's it. So let us do the integration, right? Yes. Now initially the extension, the x value is 0, that means the elongation is 0 initially. Now we want the final elongation, right? So that is taken as x only. Let's take x to be the elongation, right? The final elongation, that means that is the maximum elongation. So that is done. Okay, what is the initial velocity? 0. What is the final velocity? So that is also 0, right? Because we are finding the relative velocity, right? Not the absolute velocities of these two objects, only relative velocity, because what we used here, a, that is the relative acceleration. That means integrating that, what we are going to get is the relative velocity. But what is the final relative velocity? That is 0, right? That's what we have already observed. When it reaches the maximum length, right? The spring reaches the maximum length, then the relative velocity is 0, because both the blocks move together with the same velocity. So that means final velocity is also 0, which means the whole left hand side is 0. So that equals, so this can be easily integrated, right? So what is that? So m plus m multiplied by kx. So that if you do integration, kx square divided by 2, lower limit is anyway 0. So upper limit, if you substitute kx square by 2 minus m f x. So that's all, right? This is equated to 0, denominator we can multiply. So that's all. This will give you our required value of x. That's all, right? Equated to 0, we'll get, you can divide by x. So that will give you the value of x, that is, so multiply. So mf, yeah. So if you cross multiply, so x we need, right? So you can divide this by x, and then we will get, yes, 2 mf divided by, so this value m plus m, k multiplied by m plus m. Okay, so that's all. So that is the value of x. So that is the maximum elongation of the spring. Okay, yes. Now see, this question can also be done by other methods using momentum conservation and other things, right? So that we will do, right? But in a different chapter, right? But in this chapter we are just going to use, right, Newton's law, right? We are just using Newton's law, nothing else. We are using the spring force and then Newton's law, right? Basic Newton's law to solve this question without using any momentum or energy, right? So just the basic method we are using to get this answer. We can arrive at this answer directly if you use momentum conservation and other things, right? But without getting into that, so we are just using the basic Newton's law and the spring force to get this answer, right? So this is the maximum elongation of the spring. So 2mf divided by k m plus m. Okay. Here a block is on the ground which is attached to a vertical spring. A force F acts on this block in the horizontal direction. We have to find the distance covered by this block before it loses contact with the ground, right? Yes. When it loses contact with the ground, what will happen at that point? The normal reaction will become 0. When the block is on the ground, so there will be normal reaction in the upward direction. No normal reaction when there is no contact between this block and the ground. Alright, yes, we have to find that point or the distance covered before it loses contact. Okay, yes. Now what are the forces acting on this block? The first force is the horizontal force F, right? The only force in the horizontal direction is the applied force F. Now what about vertical direction? Gravitation force in the vertically downward direction, normal force in the upward direction, no spring force because the spring initially is unstretched, right? That is the natural length, that is 1 meter, right? That means no spring force, only normal reaction and gravitation force, they balance each other, right? So no vertical motion. Okay, now when the block moves to the right, what will happen? Now the spring is stretched now. Okay, that means there will be a spring force also, but that makes some angle, so we have to take its component in the vertical direction. What we are going to do at that point, when it loses contact, let us consider all the forces in the vertical direction. When it loses contact, there is no normal reaction, right? Because there is no contact. Normal reaction, downward we have a gravitation force, the upward force is the component of the spring force. We have to take the component. Now the spring is stretched. Okay, what is that elongation? So that is taken as y, right? L plus y. L is the natural length, so L plus y, or 1 plus y. 1 is the length, so 1 plus y is the length of that portion of the spring, right? That total. But y is only that elongation. Okay, now this is the natural length and this distance is x. That x is what we need to find. Okay, what are the forces acting on this block in the vertical direction? So let us write. See the forces on the block only. What are the forces acting on the block? So mg in the downward direction, yes, mg, minus in the upward direction we have spring force, the component of the spring force in the upward direction. The spring force is acting in this direction, making some angle theta, right? Same angle theta, right? Because alternate angle, right? So theta, that means you have to take its component. What is the spring force? First of all, that is k multiplied by the elongation. But what is the elongation? So 1 is the natural length, 1 plus y. So that means y is the elongation, ky is the spring force, but in some direction. You have to take its vertical component. That means minus ky multiplied by cos theta, right? Component. So we have to multiply by cos theta. So this is the vertical, that must be equal to 0, right? 0, because no vertical motion, because it is just about to lose contact, right? At that point there is no vertical motion, so we have to take this value to be 0. Okay, yes, that means, so we get some relation. So what is m here? So that is the mass of the object, so that is 5 kilogram, so that is 5g, that equals k. So k is also given, I think 1000 y multiplied by cos theta. Okay, yes, now we got some relation, so we can use it later. See, this is a right angle triangle, right? This is a right angle triangle, right? So the sides are L, X and L plus Y. Now what is the value of cos theta in that right angle triangle? You can find it, right? Cos theta, adjacent side divided by the hypotenuse, so we can use that. So that gives you, so 1000 y multiplied by cos theta in that triangle is L, I mean the length of the spring. So that is 1 divided by 1 plus y. 1 divided by 1 plus y. So that is 5g. So we can write it as 50, right? G is taken as 10. So what is the value of this? So 1 plus y. If you multiply, so 1 plus y equals, so 50. So this is 20 times y. So that will give you the value of y, right? So y equals, what is the value of y? So 1 divided by 19. Okay, so y is found. Okay, yes, that means what is the value of cos theta? So that can also be written, right, if required. So this implies cos theta can be written as adjacent side, that is L. So L is the length 1. Okay, so 1 divided by 1 plus y. So 1 plus 1 by 19. So that is 19 divided by 20. So we found the value of cos theta, so we can use it later if required. Okay, yes. Now what we have to find? The value of x. So how to find the value of x? So that again use the same right angle triangle. Alright, so let us take tan theta. Okay, so what is the value of tan theta? So tan theta is equal to x, so the opposite side, x divided by the adjacent side, that is 1. Okay, so x equal to tan theta, that's all. So what we want is the value of x. So x equals tan theta. But what is the value of tan theta? We know only cos theta, right? From that we can find tan theta and write this value here. See, just like a right angle triangle, what is cos theta? That is the base or the adjacent side, hypotenuse, that is 20. Now we can use Pythagoras theorem to find the other length. So this square minus this square, right? 20 square minus 19 square, right? 20 plus 19, that's all. So that is 39. So that triangle is completed. Now we can write the value of tan theta. What is tan theta? Again opposite side, right? The perpendicular divided by the base. So that is square root of 39 divided by 19. So that's all. That is the value of x. What is x? The distance traveled by this block before it loses contact with the ground. Okay, so that's all. So that is our required answer, right? What did we do? Simple. See, when there is no contact with the ground, no normal reaction. The only forces are the gravitational force in the downward direction and also the component of the spring force in the vertical direction. So these are the two forces. So that's all. So from that, these are just calculations. Okay, using that right angle triangle, we found the value of cos theta. From cos theta, we found tan theta. So that will give you the value of the required x, right? The distance traveled by this block. Okay, so that is the required answer, root 39 by 19. Here we have a bead which can move along the ring. That means it can move only along the circumference of that circle. Okay, that bead is attached to a spring. The other end of the spring is attached to the lower end of the circle. Okay, now we have to find the tangential acceleration of this bead. The bead can move only along the circle. We have to find its a tangential acceleration. Tangent, you know, right? So we have to find the acceleration in that direction. Okay, now at the moment when this angle is 60 degree, right? So that normal makes angle 60 degree. Okay, yes. So now we have to find the forces acting on this bead. What are the forces acting on this? In the tangential direction. Now we have to take the component of the spring force in the tangential direction, one force, and also we have the gravitation force mg, and then you have to take the component. See, this angle is 60 degree and also it is an isosceles triangle because this radius, right? Radius only. So radius, isosceles triangle, and also the angle is 60 degree. That means it is an equilateral triangle, right? Equilateral triangle because two sides already equal, angle is 60 degree, equilateral triangle. That means the length of the spring is also the radius of the circle, but that is not the natural length of the spring. So that is given already. What is the natural length? So that is 3r by 4. 3r by 4 is the original length. Now it is stretched and it has become r. That means what is that elongation? The elongation is this, now the length is r minus the natural length, that is 3r by 4. That means the elongation is r minus 3r by 4, which means r by 4. So that is the elongation. You understand? See, it is like this. So x here. So the final length, okay, this length of this spring, that is r minus the natural length of the spring. So that is 3r by 4. That means r by 4 is the elongation. That means what is the spring force? K multiplied by x. So k multiplied by x. So x is r by 4. So we know the spring force. Okay. But what is the angle made by that spring with the tangential direction? Because we want the acceleration in the tangential direction. What is that angle? See, that mg makes angle, see, extend that normal force. So that mg makes angle 60 degree, right? Same angle, right? The corresponding angle. mg makes angle 60 degree with the normal. So mg makes what angle with the tangent? So that is 30 degree. So mg cos 30 is the component in the tangential direction. Similarly, this angle is also 30 degree, right? 60, 30. So that means the kx means the spring force that makes angle 30 degree with the tangent. So that means kx cos 30. So that is the component in the tangential direction. Similarly, mg cos 30. You understand? So the total force acting on the block on this bead in the tangential direction is due to that spring force. So that is kx cos 30. Kx cos 30. So that is the force. And also mg, the component of mg. So mg cos 30. So plus mg cos 30. This is the total force in the tangential direction. So that must be equal to mass times the acceleration. Okay, so that's it. Substitute all the values that we know. So we can get the answer. So k value is known in the question, right? So from the question, so mg by k, mg by r. So that is the value of k. Okay, and x value we have found. So that is r by 4. Cos 30. So that is root 3 by 2. Plus again mg cos 30 is root 3 by 2. So that is mass times the acceleration. So what do you get? So we can simplify this. This r gets cancelled. Okay, so g. So root 3 by 8. Okay, m. Okay, if you take mg out, you will get r gets cancelled, root 3 by 8 plus okay, again, so root 3 by 2, so that equals mass times the acceleration. That will give you the acceleration. So this is for 5 root 3 divided by 8. So m gets cancelled. So 5 root 3 divided by 8 multiplied by g. So that's all. So that is the required acceleration, okay, in the tangential direction. That's all. So that is done. So we have considered all the forces in the tangential direction. Now we want to find the normal reaction between the bead and that ring. So that means you have to consider the forces in the normal direction. Okay. So what are the forces acting in the normal direction? So this is the tangential direction. The tangential direction. So now we will consider all the forces in the normal direction. What are the forces acting in the normal direction? So take this to be positive, n, the normal reaction, so that is n. And also the component of the spring force in the normal direction, that angle is 60 degrees. See, it is an equilateral triangle, so 60 degree. So take its component, so 60 degree, cos 60 is to be multiplied, so kx cos 60. So n plus kx cos 60 degree. And also the component of the gravitation force, right, the weight in the normal direction, but in the opposite direction. So 60 degree the angle, so mg cos 60 in the opposite direction. So minus mg cos 60. So this is the total force in the normal direction. So that equal to 0 because there is no normal acceleration, because the bead is moving along the circumference. That means there is no normal acceleration or normal displacement. So that's all. So this will give you n value. That's it. So what is n value? Or n plus kx. Again you substitute the same value. So what is the value of k? mg by r, and x is r by 4, and cos 60 is 1 by 2 minus again mg cos 60 is 1 by 2 again. So that equals 0. So this will give you our required normal reaction. So this is mgr gets cancelled again. This is mg divided by 8 minus mg divided by 2. So 1 by 2 minus 1 by 8. So that is 3, right? So 4 minus 1, 3. So 3 mg divided by 8. That's all. So that is the normal reaction between this bead and that ring. So that is 3 mg divided by 8. So that is the normal reaction, and this is the acceleration of this ring in the tangential direction. Okay, so that is the answer. Here the system is in equilibrium. There are two blocks. The block of mass 2m is attached to a vertical spring, right, and these two blocks are connected by a string. Okay, now suddenly the string is cut. Now we have to find the initial accelerations of these two blocks. Okay, yes, what are the forces acting on these blocks initially when the system is in equilibrium? So when the system is in equilibrium, what are the forces acting on these blocks? So the lower block of mass m, so the forces are mg in the downward direction, mg, and then the upward force, so that is the tension due to the string only. So that means mg minus t, so that equals 0. So this is for the block m. Similarly for the block 2m, so what are the forces? Now the gravitation force mg, 2mg, and then the tension force due to the string, that is in the downward direction, so that is plus t, and also the spring force in the upward direction, so that is kx, so in the opposite direction, so minus kx, so that equals 0. Okay, so these are the forces acting on the upper block. Now we don't need the tension, so we can just add these two. Okay, if you add these two, so we'll get mg plus 2mg, so that is 3mg equals kx. Okay, that's it. So this will give you our required value of x. X means the elongation of the spring initially, right, when the system is in equilibrium. So that is done. Now when the string is cut, okay, now the string is cut. Okay, now what will happen? The tension becomes 0 suddenly, right? String is cut, that means no string, so suddenly the tension becomes 0. So now what are the forces acting on this block of mass small m? So what are the forces acting on the block small m? Actually it is a free fall, right, because the only force is the gravitational force. If you want, you can write the equation, or directly we can write the acceleration. Let me write it. So mg is the only force, no tension. Tension becomes 0. So mg is the only force, that equals mass times the acceleration. That means the acceleration. So let me write am, write the acceleration of the block of mass m. So am equals g. Okay, that's all. G is the acceleration. So that is known, right, already, because there is no tension, only the gravitation force. So acceleration due to gravity g. So that is for the lower block. What about the other block? So 2m. Yes, what are the forces acting on this block now? Again, the tension is 0, right? Tension due to the string is 0. Now what are the forces? Gravitation force. So that is 2mg in the downward direction. Okay, 2mg minus kx. Kx due to the spring in the upward direction. So minus kx equals mass. Mass is 2m multiplied by the acceleration. Acceleration can be written as a2m. Okay, yes. This kx is already known, right? We know the value of k. That's what we found here. K or kx directly we can substitute. Kx is 3mg. So that we can substitute here directly. So that means, so this gives you the value 2mg minus this kx is 3mg. So that equals 2m multiplied by acceleration of this 2m. So that's it. So we can write the acceleration of this 2m block. So that equals so what do you get? 2mg minus 3mg, which means minus mg divided by 2m. So which is minus g divided by 2. That's all. So that is the acceleration of the upper block, minus g by 2. Minus because it will move in the upward direction, because we have taken the other one g. That means the downward direction is taken as positive direction. So that means minus g by 2. So this block will move in the upward direction, right? See, obviously, right? So due to the spring force, it will move in the upward direction. So having acceleration g by 2, the magnitude is just g by 2, but in the upward direction, and the acceleration of the other block is just the acceleration due to gravity g. That's all, right? So these are the accelerations of the two blocks immediately, right, after this string is cut. Okay, the accelerations are g and minus g by 2. So that is the answer. This question is nothing different. We have to use the same idea that we used in the last question. So what are the forces acting on the upper block when the system is in equilibrium, right? So the weight in the downward direction and also the spring force in the downward direction, the tension is acting in the upward direction. Similarly, for the other block, the spring force is acting in the upward direction, right? And the weight in the downward direction, right? So that's all. These are the only forces. So we don't need the tension. So that means you don't need to consider the upper block. Only the lower block is enough, right? See, when the system is in equilibrium, then the forces acting on the block of mass m, so that is the weight, gravitation force in the downward direction mg minus the spring force, so kx, so that must be equal to 0. So this gives you the value of kx, so that is mg. Okay, so we can get the value of x, right? That means the elongation of the spring initially when the system is in equilibrium, so that is mg divided by k. Okay, now when this string is cut, that means the tension becomes 0 immediately. Okay, so no tension force is acting on this upper block. So what are the forces acting on the block? So now we will calculate for this m. So what are the forces acting? Now the mg, right, gravitation force in the downward direction, so mg, and also the spring force, so that is also acting in the downward direction, right? The spring force is also in the downward direction, so plus kx, that equals mass times the acceleration of that block, so that is m. Okay, but this value of kx is already found. Okay, from this we can write the value of kx, so that is small mg, so that is okay, so mg plus small mg equals m times the acceleration of m. So that's all. That gives you the acceleration of the upper block of mass capital M, that is m plus m multiplied by g divided by capital M. So that's all. So this is the acceleration of the block of mass capital M. Similarly, we can write all the forces acting on this other block, right? So again, the weight in the downward direction, so that is mg, and the force due to the spring, that is in the upward direction, right, opposite direction, so that means minus kx, that equals mass times the acceleration of m. Okay, but what is the value of kx? So that is already known, so mg only, so mg minus again mg, so that equals mass times the acceleration of m. So that gives you the value of acceleration of m, so that is mg minus mg, that is 0. So 0 is the acceleration of the lower block, right? 0. which means it is at rest, right, for that moment only at the moment immediately after the spring or the string is cut, that block is at rest, then it will start moving, but initially the acceleration is 0. You understand, because these two forces balance each other, right? The upward spring force and the downward gravitational force balance each other initially, right? You understand, at that particular moment the acceleration of the lower block is 0. All right, so that is the answer. The lower block has acceleration 0, the upper block has acceleration m plus mg divided by m, right? So that is the answer. This question is similar to the last two questions. So here the spring is cut instead of the string, and also we have 3 blocks. All right, so but the idea is almost the same. So here, so what are the forces acting on these 3 blocks, right? Let us do it one by one. See, first of all, this system is in equilibrium. So what are the forces acting on this these blocks, right? First case, when the system is in equilibrium. Okay, so that means, so what are the forces acting on the block of mass 2m? 2mg gravitational force in the downward direction. Now we have 2 springs, right? So this means we have to know the elongation of these 2 springs, right? So the upper spring, suppose it is elongated by a length of x, okay, and the lower spring, so y units, right? That is the extension. So x and y. So that means what is the spring force in the opposite direction? That is kx, right? So 2mg minus kx. All right, and also the tension due to that string, right? So the string which connects the 2m block and 3m block, that has tension, say T. So then the tension is acting in the downward direction, so that means so plus T. So that equals 0. Initially the system is in equilibrium. Okay, so that is for the block of mass 2m. Similarly, the next block 3m. So what are the forces here? Now again 3mg, and also the tension force in the upward direction, so minus T, and also okay minus T, and the spring force due to the lower spring, so that is in the downward direction, so that is plus ky now. So y is the length we have taken, so that is 0. Okay, now the last one, so m, so that has mg minus the spring force, so minus ky. So that equals 0. So that's it. So this is when the system is in equilibrium. So these are the equations. Okay, done. Now the spring. Okay, so this time the spring is cut, the upper spring. Okay, the spring is cut. So immediately what is the acceleration? So let us find it. See here, now when the spring is cut, so here the situation is a little different. See, when the spring is cut, immediately the acceleration, the tension will not become 0. Okay, see, the upper 2 blocks, right, the block of mass 2m and the block of mass 3m will move with the same acceleration, right? So same velocity or at the same acceleration. Why same acceleration? Because if they move with a different velocity, okay, if they move with a different velocity, then the string which connects them, that will become slack, right? So only when these 2 blocks move with the same acceleration or the same velocity, so will this string be taut. You understand, that string connecting them will be taut only when these 2 move with a different velocity, right? Move with the same velocity. See, are the acceleration. So acceleration of the upper block 2m and acceleration of that block 3m. Okay, so they move with the same velocity or the acceleration, right? Same acceleration. Okay, so remember, so this is little different compared to the other one. Here, so these 2 have the same acceleration. Now let us write. That means you can combine these 2 blocks and consider them as one system because they move with the same acceleration. They are always their relative velocity is 0, right? That means they always move together. So we consider this 2m block and 3m block as one system. So for that 2m plus 3m block, 2m plus 3m block. So let us write the forces acting on this. So instead of writing the blocks m, 2m separately, 2m plus 3m block together, what are the forces? Now that is the gravitational force in the downward direction. So that is 2m plus 3m. 2m plus 3m g, right? That is the weight, right? Gravitational force. Total is 5m g in the downward direction, and also the spring force, so that is plus ky. That equals mass. Again, mass is 5m. Acceleration of that 5m. Okay, acceleration of 2m you can take. or 3m, anything, both have the same acceleration. Okay, so this will give you the value ky. Ky is known. What is the value of ky we found? Mg. So that means this is 5 mg plus this is mg, that equals 5 times the acceleration of m a to m. Okay, yes, done. So that will give you our required acceleration. Sorry, this is 5m. Okay, 5m multiplied by acceleration of this. So that will give you our required answer. The acceleration of 2m block equals, so 5 mg plus mg, 6 mg divided by 5m. So that is 6g divided by 5. Okay, so that is the answer. If acceleration of 2m block is this much, then the acceleration of 3m block is also same, because we have taken these two values to be equal. So acceleration of 3m block, so that is also 6g divided by 5. Okay, now what about the acceleration of the lower block of mass m? Okay, now let us write the forces acting on that block. What are the forces? Now mg in the downward direction minus the spring force in the upward direction, that is ky. So that equals mass times the acceleration of m. So but ky is already what? 0. Sorry, ky is mg, that means that will become 0. So mg minus mg, so that will become 0. So mg minus mg equals mass times acceleration of m. So that means the acceleration of m equals 0. See, it is just like the last question. So there also we got the acceleration, because these two forces balance each other. So immediately when this the spring is cut, so the acceleration is 0. So the acceleration of the lower block is 0. The other two blocks have the same acceleration, which is 6g divided by 5. Okay, so that is the answer. So that's about the spring force. In the next class, we'll start frictional force. Okay.